Service. Welcome back. Online familiarization workshop, online sensors, and optoelectronic devices. Myself, Preeti Majumdar, and I am Mitali Bosha. So this session will be on nanomaterial simulation tutorials. So the first talk will be delivered by Professor Pankaj Kumar Mishra on a basic introduction to density functional theory. So Dr. Pankaj Mishra is a theoretical condensed matter physicist affiliated as an associate professor at physical department at IIT Guwahati. After finishing his integrated PhD from IIT Kanpur in 2011, he went for a couple of postdocs, first from INUP Paris, France, and second from Weizmann Institute of Science, Israel. Before joining IIT Guwahati in 2016, his research interested into statistical aspects of condensed matter system. In recent years, he is mainly interested in different aspects of Bose-Einstein condensates, such as quantum droplets, Anderson localization, quantum turbulence, and related fields. Over to you, sir. Sir, could you hear us?
Hello, can you see my screen?
Yes, sir.
The person you are speaking with has.
So can you see my screen now?
Yes, sir.
Okay, so I don't know that what is happening, because once I move, somehow my team gets crashed. So if it continues, then I'm really very sorry. Then what I'll do, I'll send the slide to you, so maybe you can display and I can speak. But let me first go ahead with by sharing from here. Okay, so let me begin my talk by thanking organizers for giving this unique opportunity for presenting my thing in this workshop. My theme of the presentation is a little bit theoretical in nature. So Professor Pamu just told me that just introduce the density functional theory at the very, very basic level. So I have tried to keep my talk at very, very basic level, and I will go through very simple stuff. I'll do very simple stuff related with first many body theory. And then slowly I'll move to the necessity of density functional theory, and I'll speak about different sort of theorem and the kind of limitation that we have in the density functional theory. Before going ahead, so this will be my plan of the talk, that I'll first introduce the density functional theory, then I'll speak about this Hartree-Fock method for many electron system. What are the advantages and disadvantages using this particular method? And then I'll move to this historical, I'll give some little bit flavor of historical background of density functional theory. In that case, I'll discuss about Thomas-Fermi approximation, Hornberg-Kohn theory for DFT, and Kohn-Sham formulation. And further, in the DFT, there is one particular entity that basically needs to be approximated, that is energy correlation. And for that, different methods are available in the literature. So I'll mainly discuss two simple methods. One is local density approximation, another one is generalized gradient approximation. And then I will also discuss about the limitation of DFT that I am discussing here. And if time permits, I will discuss one of the work that me and Professor Subhash Tota from our department did with Dr. Sayandeep Ghosh. So he did PhD with us, and following my talk, he'll be giving hands-on session on this density functional theory, how to use the density functional theory using VASP software. So before going to the main presentation, I just want to introduce you my group. So we work on various aspects of ultra cold atoms. So we work at the temperature which is around 9 Kelvin, and in that case we get the Bose-Einstein condensate. But we look at things at the theoretical level, and right now I'm using the mean field theory known as Gross-Pitarski equation, and these are the students working on that. And I had the collaboration with Professor Subhash Tota also, with whom I started using the density functional theory and looked at several aspects of magnetic materials, and these are the three PhD students that graduated using those DFT stuff. So first, let me introduce you. Let me take you from very basic of the quantum system. So as we are aware about, when we try to describe the quantum system, then generally in the Schrodinger picture, we can describe it using the state function that is denoted as psi here. And this psi is a complex quantity, but generally the physical observable is probability density function that is defined as mod psi square. It gives us the probability of finding the particle between r to r plus dr. So here, this is a pictorial diagram through which we can see if we want to find out what is the probability of finding a particle between this region, then we need to first find out this wave function, and then we have to take the modulus square of this wave function, and then we have to multiply this width, and then we can detect that this is the probability of finding the particle at this region. And generally this particular wave function depends upon the particle position. So suppose if you have one particle, then it will have the one particle coordinate and time. And if you have n number of particles, then we have 3n number of coordinate that it will depend upon. Similar way, if we talk about this density, then as I mentioned that this is modulus of psi square gives us the density. So if we multiply this thing with this all the position of the particle, if we integrate over, then this gives a density of finding a particle at a position r. So here we are dealing with the many particles. Let's say there are n number of particles, and corresponding to that n the position vectors are there. But when we discuss about this density, then it depends upon only three variables. So wave function is generally the variable of n number. It is a variable of n the particle, but and so it has a three n number of variables. But we have the density which depends upon only the r. at a given point. So it can be described using the 3 variables only. So that is the advantage that we have. And if you consider the spin of the particle also, then the per particle 2 extra degrees of freedom for the spin will get added up. So if we try to basically solve the system, then we need to solve the Schrodinger equation for this many body system. So as we are aware about, for one electron system, we can solve the Schrodinger equation quite easily. But even we go for 2 electron system, then we know this thing that how difficult it become to get this exact value or to get the analytical solutions. Then we rely over many approximate method known as the central field approximation and Hartree-Fock scheme. So so those are things we have to do. So but what we do in the density functional theory, our main variable is density of the system. So in that case, instead of dealing with the wave function, which is the function of the position of the n number of particles, now we only deal with the density, and that is a function of only 3 variables. So DFT is the computational quantum mechanical modeling method used in physics, chemistry, material science. I'm just naming few of the area in which it is quite widely used. It has used in various other fields also, like people use in astrophysics, in biology, they use it quite rigorously. So mainly we use this thing to investigate the electronic structure, and the kind of thing that I am going to discuss today, we'll be discussing mainly the DFT used for the ground state configuration. There are still some development is going on to get this DFT for the excited state, but right now our theory can only give us the idea about the ground state of many body system. So just give you this historical flavor of this development of the density functional theory. So it is started with the work of Thomas Fermi model in 1920. And then in 1964, Hohenberg and Kohn provide a very beautiful theorem, and that we will discuss in today's lecture. And to that, they establish that corresponding to each wave function, there is a unique density. And that density you can always use to describe the system instead of dealing of the wave function. So that gave a lot of convenient to deal with the many body theorem, many body system. So we will discuss those aspects, that how basically it gave this kind of advantage over this dealing the system with Hartree-Fock method. And then in 1965, Kohn Sam basically introduced the scheme in which they basically converted the interacting electron system in like a effective non-interacting electron system using the pseudo potential. So we'll discuss about those things. And then there are several schemes being introduced to describe the pseudo potential in more appropriate way, like local density approximation, the GGA, and so on. And this DFT the advancement, or the DFT introduction in the field of material science brought Nobel Prize for Walter Kohn in chemistry in 1998. So before going to the many body theory, I just wanted to mention the kind of thing that we are dealing here. We are using the Born-Oppenheimer approximation. So in that case, we consider that we consider the whole system, which include the nucleus as well as all the electrons. So we have the kinetic energy corresponding to nucleus, this kinetic energy corresponding to electron, then nucleus particle interaction energy, then electron energy, and the nucleus electron energy. So we have all sort of energy, but the main assumption is being considered that the mass of the electron is very, very small compared to the nucleus. So dynamics for the electron that we can totally take it separately compared to the dynamics of the nucleus. That gives us the advantage that we have the wave function in which this wave function only depends upon the position of the nucleus. So we can assume that for a given position of the nucleus in the system, we have to only solve the Schrodinger equation corresponding to the electronic wave function. So so basically whatever we'll be dealing so far beyond this point, we'll assume that we are assuming the Born-Oppenheimer approximation, where we are just separating the dynamics of the electron completely from the dynamics of nucleus, considering the fact that electron dynamics happen at very fast time scale compared to the nucleus dynamics. So using that, let me first take the step from very beginning. So here I am discussing the thing where we have n number of the electron present in the system. So this is the Hamiltonian corresponding to that. This is the kinetic energy, this is the potential energy, this is the electron-electron interaction that we have. So psi will depend upon position of the electron, R1, R2, R3, Rn are the position of the electrons. So let me first start the things for very simple system in which we have the two electrons only, that is the helium-like atom. So we have the kinetic energy of one electron, kinetic energy of second electron. This is the potential energy, the interaction of that first electron with nucleus. This is the potential energy corresponding to second nucleus, and this is the interaction part of the energy. So this is a Schrodinger equation for the two electron. But we know this thing that if this term was not present, then we have the solution. But due to the presence of this interaction term, we don't have this exact solution that exists for helium atom. Solved numerically using various techniques, but this calculation cannot be done routinely, or there are no analytical solution available for helium-like atom. So how to proceed that? So there are several schemes. One of the scheme is known as variational principle. So where what we do that we start, we guess the wave function, and then we calculate this particular function, and we keep on iterating this function until we reach to the ground state. So, in that way, the whole thing depends upon how do we gauge this wave function at the initial stage. So now let's have the wave function in which we assume that these two electrons are the simplest one that we can consider here. That these wave functions, these particles are independent to each other. In that case, the simplest wave function that we can begin with is the hydrogen-like atom for one electron, and this is for second electron. So the wave function we can begin with this product of these two wave functions. If we calculate the energy corresponding to that, that is that comes minus 2.8477 in atomic unit. So, but if you look at the ground state energy of the helium, that is very far away from this energy. So this approximation doesn't hold. And the reason behind that is that we are not taking into account of the electron-electron interaction. So how to include that the electron-electron interaction? So that we can include by taking into account of the interaction. So here, the first thing we are basically taking into account that these electrons are indistinguishable, so it can take a position R1 and R2, and also we have the interaction between the nucleus of the one electron and the other electron, that we are denoting zeta 1 and zeta 2. So our wave function is a superposition of these two product of the wave function. So if you do that, then what we see that we get the in a ground state energy which is very close to the experimental value. So in this case, what we basically see, the wave function is not a product wave function. It has a built-in correlation between the two electrons. So here we are taking into account of the correlation, and correlation parameters are zeta 1 and zeta 2. So this zeta 1, zeta 2, what we can see here, that zeta 1, R1 we are taken here, zeta 2 and zeta 2 is coming with R1. So zeta 1, zeta 2 are the parameters, correlation parameters, and to that we are taking into account of the correlation between the electron through this particular wave function. So the wave function can be generalized to more number of electrons. So here we have discussed this thing for 2 electron, but this thing we can generalize for the more number of electron. And what we see that it will become more and more cumbersome if you get more and more complicated to guess with for if you go for heavier and heavier atom, because even for 2 electron we can see here that we have wrote this thing just by guessing between this correlation. If you go for 3 electron, then we have the 3 parameters, then we 4 electron 4 parameters. So it will keep on increasing, and then we have to make sure that electrons should follow this anti-symmetric wave function. So such kind of difficulty comes while dealing with this kind of variational approach for many electron system. So to overcome that particular limitation, we have the Hartree-Fock theory that basically says that if we know the wave function corresponding to the independent system, so like phi 1 R1, phi 2 R2, phi 1 phi 2, these are the wave function corresponding to the non-interacting system when the corresponding to that electron equation R1, R2, R3, and Rn. So we can write the total wave function as a product of these. And due to that, the electrons are treated like moving independently in the average field, and that average field we are just approximating with this particular function. So what we basically see that we assume that each electron is basically moving under some central field that is generated due to the nucleus and the presence of the other electron. So in that that is also known as central field approximation. In that approximation, we have this the Schrodinger equation will get converted into this is a V external, and this is the central field that each electron will see. So that depends upon this density. So then question arises that we can find this energy corresponding to Hartree-Fock. So this is the kinetic energy for the independent electron. This is the kinetic energy. This is the potential energy due to the of the electron, and this is the correlation term that take into account of the electron-electron interaction, and that is coming due to the interaction between the electrons. So again, if we use this variational principle, then we can basically get the corresponding wave function, but or corresponding solution. But the question arises: can we work within the domain of product wave function and still get good wave function for electrons? So the answer is yes. In Hartree-Fock method, what we see here that when we write the Slater determinant, then we take into account of the Pauli exclusion principle, that total wave function will follow the Pauli exclusion principle. So because of this principle, electron of the same spin state stay away from each other, and no two electron of having the same quantum number can be filled up in the same state. So the principle requires that the wave function be antisymmetric with respect to the exchange of two electrons. So that is taken care by this particular determinant formulation of this Hartree-Fock wave function. And here we can take into account of this spin state also denoted by alpha and beta. So in that way, this is the final form of this Hartree-Fock Hamiltonian. And what we basically do here, that here we take into account that we have the central field, that is the mean field, under which each electron basically is subjected to. So this is some sort of mean field approximation under which we are working. So in that case, we have the Hartree-Fock equation that will have this form. So here, this equation looks like the independent electron equation, and we have this the correlation term that depends upon the density term here. So in the Hartree-Fock method, there are two other terms arise. One is the Coulomb interaction, another one is exchange effect, and that the effect come in terms of this particular part, and this correlation part. So why I want to highlight this part, that because when we go to this density functional calculation, that we'll see that we will try to basically devise a scheme similar to the Hartree-Fock method, but here unlikely here we are using the wave function, but in density functional theory we'll be using this density as a variable. But we will try to devise a similar kind of a scheme where we will, under the mean field approximation, we will convert the interacting system into the non-interacting system, and but there also we will have this correlation energy that will come into picture, and we need to model that correlation energy. So, so overall, what we find that Hartree-Fock theory is the best mean field prescription of the many electron system. The question arises: can the non-local exchange potential be replaced by a local potential? Because what we can see here that this potential is non-local in nature. This the exchange potential that we are getting. So can it be replaced with this? Local potential? That is one task, because what we know here that calculating the non-local thing is quite expensive in nature. So we always try to somehow convert this problem into the calculation at the local level. So, so what are the things that we get? So here I have just listed few of the atom that energy can be calculated using the mean field approximation Hartree-Fock method. So here for one electron atom, we get the exact value using this Hartree-Fock method. There is no difference between experiment and Hartree-Fock. In helium, the difference is 1.4%. In beryllium, the difference is 0.65%, and this keeps on varying as we go for larger and larger electron system. So, the question arises that can we again use this particular method for let's say many electron system, because when we deal with the materials, then we have this large number of electrons that we have to deal with. So, so then Hartree-Fock method becomes little bit outdated or more difficult to handle when we go for when we go at the material level. And why it is so, as I already discussed, that wave function is described by 3n spatial variable and n spin. So there are 4n variables are involved. So in that case, we can see that if we go even for go even for n number of electrons, so go even for, let's say, 10 electrons, then we have the 40 variables that we have to deal with. And suppose if you make the discretization and each point, then even for 100, it is a lot of computational power that we need to deal with. So, so the question arises: can we replace the wave function by a simpler quantity? So the answer lies yes, and that I already introduced that we can deal with this the electron density that only depends upon the 3 variables. Instead of 3n, now it depends upon only 3 variables. So this is the pictorial diagram through which I just distinguished between these two schemes. So this is the scheme used in the Hartree-Fock mean field approximation. This is the scheme used for this density functional theory, where we deal with the density of the electron instead of dealing with this wave function. So let me take you at this point that some of the historical background for DFT that basically led people started thinking in the direction that we can use this density. We can describe a system in terms of density instead of taking up in terms of the wave function. So the first, this kind of approach has been proposed independently by L. Thomas and E. Fermi in 1927, known as Thomas-Fermi model. In that model, what is being assumed that multi-electrons, the atom at zero temperature just obey the Fermi-Dirac distribution, and then there is a maximum occupancy up to which we can assume that the orbiter is filled. So in that case, we can consider degenerate Fermi-Dirac fluid, which is held in the condition of hydrostatic equilibrium, and there is a balance between the pressure gradient and electrostatic force. So with that, we can get the maximum wave vector up to which the electron will be filled, and this is known as Thomas-Fermi momentum. And that depends upon the density of the electron. It is semi-classical theory because here the momentum is considered as a function, not as an operator. So using that, we can write the Thomas-Fermi energy. This is first part is the kinetic energy, and the second part basically takes into account of the electron-electron interaction. So here this is the electron-electron interaction, and this is the electron in presence of the external field. So in that case, we have the kinetic energy and the potential energy that contains two parts, external field and electrostatic interaction. Again, what we can do here using the variational scheme, we can get what will be the equation of motion, and the equation of motion we can get that what will be this the wave vector that depends upon the density. So finally, we can do a little bit more and can get the time dependent equation corresponding to that, and those equations are quite widely used to get the photoabsorption curve for the atoms. So now let me take you through the result the theory corresponding to the density functional theory. So what we basically saw that instead of dealing the system with the wave function, we can describe the system using density. But then question arises, is there any one-to-one correspondence between dealing the system using wave function and the density? So there is a very beautiful theorem known as Hornberg-Kohn theorem, and that gives us this idea that for a given particle-particle interaction, the ground state density rho of a system gives the external potential Vx star or ground state wave function uniquely. So it basically tells us that for the ground state density, that through that basically we can uniquely that ground state density can uniquely associated with the external potential as well as the ground state wave function. So how to prove that thing? Here we'll prove this thing using some contradictory way. So first we assume for this case, they assume two different potential having potential V1 and V2, and that gives the same ground state density rho r. So here H correspond to the Hamiltonian for the potential 1 and potential 2. So for these two potential, we have the two wave functions psi1 and psi2. So question arises that can psi1 and psi2 are different, but can it give to the same density? So the answer will be yes. So for the ground state, for a given the density, there will be unique the wave function and unique external potential that we are that we want to basically establish here. Then only we can convert our problem in the equivalent manner, that the problem dealing with the psi, which has a 3n variable, or problem dealing with density, which has only 3 variable, will give us the same result. So here, this is the expectation value corresponding to the psi1 wave function. So we can write it psi1 h1 psi1. If this is the ground state corresponding to the psi1 function, so this will have the less energy compared to this the expectation value of this Hamiltonian corresponding to psi2 wave function. So we can write it S2 minus V2. This corresponds to the V2 potential corresponding to the psi2 wave function. So eventually we have this the E2 plus this is the expectation value of V1 minus V2. Similar way, we can have the E2 that correspond to the ground state energy corresponding to the psi2 wave function. We can use the similar sort of technique, and we can get it as E1 minus the expectation value of V1 minus V2 potential with respect to the ground state density rho r. But what we get here, we are getting positive sign here and we are getting negative sign here, and E1 and E2 should be same because it describes the ground state energy. If this is the case, then we get this identity that E1 plus E2 is less than E1 plus E2, and this is the contradiction that we are getting. So that gives us this picture that for a given the density of a ground state, the corresponding wave function will be unique, as well as the corresponding external potential will be unique. So it is safe to use density to describe the whole system instead of taking taking wave function as a variable. So now we have just converted the problem in the reverse way. In the Schrodinger picture, we had the psi as a variable, and then we compute the density. But here in the DFT picture, we have density as a variable, and using the density, we will calculate the wave function as well as the energy. So our wave function will now become the function of density. So it will become a functional. That's why it is density functional theory. Our energy will become the function of density. So energy becomes density, function of density, and density is a function of space. So that's why it is density functional theory, and the name was given. So the conclusion is that the two different potential cannot give the same ground state density. So there is a one-to-one correspondence between this rho and external potential and psi. So here now psi will depend upon R and rho depends upon R. So that's why you can see that psi is a function of rho and rho is a function of R. So it is a functional of the ground state. So property of a system can be expressed as a functional of the ground state density rho r. So in that case, again, we can use the similar kind of technique that we discussed in the case of Hartree-Fock scheme. You can use the variational principle, but now our variable is density. So so psi will be written in terms of the density because we know first the density, then we calculate psi. So so in that case, our energy will be function of our density, and we can use this Euler-Lagrange scheme that is just reminiscent of this Thomas Fermi equation that we dealt with, and can calculate the kinetic energy, this electron-electron interaction, and the external potential. That will be function of the density, and we can have this Euler equation for the density. So, so thing is that here we have a lot of approximation that is involved again. First thing is that kinetic energy has to be approximated as we did it in case of Thomas Fermi. So what we assume that there is a maximum energy that can be the Thomas Fermi energy of the electron. So what we can see here that kinetic energy in that case has been assumed that the electron distribution is homogeneous in nature. So accordingly, kinetic energy is approximated. And the Coulomb energy can be calculated directly. However, exchange and correlation energy are calculated approximately because we don't have any idea with this approximation how to calculate this the exchange and correlation energy. So since kinetic energy is an important component of total energy, its approximation affect the result significantly. So orbital nature of the atoms is not obtained in the Thomas Fermi theory. So if we consider the cell-like structure of the atom, that at different orbital, if you want to compute the theory, then this picture will not be valid, because we are considering that electron distribution is same for all the orbital. So in that case, some better theory is required to treat the kinetic energy. So in that case, there was a development done by Cohn-Sam, and there is also popularized with Cohn-Sam formulation. So it started with the motivation that we need to look at an equivalent non-interacting system of particles that will yield the same density as the interacting system. So that we basically saw in case of Hartree-Fock method also, that we converted the interacting system using the central field approximation to the non-interacting system in presence of the mean field. So similar kind of thing was developed by Cohn-Sam under the Cohn-Sam formulation. So this is the energy in the Cohn-Sam formulation, and here this is the kinetic part, this is the Coulomb interaction, and this is the exchange interaction between the electron, and this is the potential. This is the energy due to the external potential. So what we basically see here, that again the more probabilistic term here to approximate this exchange correlation, that is not known, that how to calculate this thing or get this thing exactly for the given system. So from now onward, our whole focus will be on to calculate this exchange correlation exactly for the density functional theory. So what we see here, if we have this calculation, if you know this energy, then we can basically get this Euler-like equation again for the density, and this is just this part simply describes the non-interacting kinetic energy. This is this one is Coulomb interaction, and this one is the exchange correlation that I was discussing in absence of any external field. So the whole problem here boils down to solve this sort of equation in which what we basically consider here, that this the whole part we consider as a V effective. So this V effective contains the external potential, Coulombic interaction, and the exchange correlation between the electron. That is that is important to calculate. So what we see here, that for a given density, always we can calculate this effective potential, and then we can solve this equation. So this equation can be solved in that way self-consistently, so that we can start with the gas density, and then we can keep on solving until we reach to the ground state energy. So in that way, Cohn-Sam approximation just convert the whole DFT equation into the equation corresponding to the non-interacting system with an effective potential. And the main energy of material scientists basically goes to model this particular effective potential. And there are several schemes through which we can model this correlation function. So here exchange correlation energy to be approximated. So there are several schemes to deal with such kind of thing. One is known as the local density approximation. So here exchange correlation function are often written in the following form. So written as exchange correlation density times density, and this exchange correlation density is again being approximated in two ways. In one case, we take this this part as a energy per electron for a homogeneous gas of density, just like a Thomas Fermi approximation. And this part we get it some Monte Carlo simulation, and that will be based upon the material. So, so in that way, there are several expressions for the correlation of this part. This part we can see that it is directly coming from the Thomas-Fermi approximation that we can get from quantum Monte Carlo simulation for the uniform electron gas. There are another scheme which is known as generalized gradient scheme. So instead of making the approximation that our density is uniform, we can take into account that there is some small inhomogeneity present in the system. So that can be approximated using this by taking the first gradient of the density. So an improvement in the accuracy provided by the LDA can be obtained by generalized gradient approximation functional. This function depends not just on the value of the density at the point, but it also depends upon the gradient of the density. Okay, so this is the first order approximation. We can take into account of the higher order approximation and can basically modify our calculation and can see when we are getting this the result very close to the experiment. So this is just the pictorial diagram that I have given, and that is being used for this numerical simulation calculations. So we start with the initial guess of the density, then we calculate the effective potential corresponding to that, and there is a particular model that we use to calculate this exchange correlation. Once we have that, then we have this Kohn-Sam equation, and the Kohn-Sam equation we solve, and we get the wave function corresponding to that. Once we have the wave function, then again we calculate the electron density and the total energy. So first we calculate the electron density, and then the total energy will depend upon the density, and we see that whether the energy has been conserved or converged or not. If it has not converged, then we again repeat this process. In that way, we keep on doing this simulation until we get the converged state, and finally we have the output that basically gives us the energy corresponding to the ground state of the system and the density. Then question arises, what are the limitations of density functional theory? So the first thing that we realize that we are using this mean field approximation. So we can only deal at present for the ground state. We don't have the proper theory that can deal the system at a finite temperature. So we are not equipped enough to deal for the excited state. So what is the disadvantage for that? That Hornbeck-Kohn-Sam theorem is not valid for the excited state. So band gap in semiconductor insulators are always underestimated. So we cannot get a clear picture about the semiconductor and insulators. So possible solutions there are different hybrid functionals schemes are available, which basically club this density functional theory calculation with molecular dynamics simulation, molecular dynamics, dynamics, and then they basically develop this hybrid functional scheme to deal with that. Then we have this some approximate scheme also, LDA plus U, that Sandeep will discuss in his presentation. And there are several other schemes, GW, SIC, that increase the correlation gap, and that then we are able to clearly take these things, semiconductor insulators, in the better way. And then we have the several schemes that basically gives us some the upper hand to overcome this particular limitation of DFT, that is overbanding. So the local spin density approximation is yields basically too small lattice constant, and it has a too large cohesive energy and too high bulk moduli. So if we want to get this mechanical behavior of the system using this local density approximation, that then give us a good result. Then the possible solution will be to use this gradient, the generalized gradient scheme that we discussed, and it gives us the advantage over local density approximation in terms of calculating this overbanding, the binding between the different atoms. So the use of GGA is mandatory for the calculating the absorption energy, but the choice of correct GGA is also important. The another limitation of DFT is is a lack of a strong correlation in the system, because the scheme that we have discussed, especially this Kornberg-SAM scheme, that is valid for the weakly interacting system. But as we understand that we have many heavier atoms that have this d and f orbital present. In that case, exchange splitting will be more narrower, and this DFT, the simple DFT will not work. So in that case, the one limitation comes that the DFT basically gives us metallic state. So to overcome that particular situation, DFT plus U scheme being used, where U takes into account of the Coulombic interaction. So in his in the next presentation given by Sandeep Ghosh, he will discuss more about this U. But at present, this particular parameter U is taken as a free parameter. There is no direct theory which can tell us that what will be the U for a given material. So I will show some result where we will show that we have taken some free parameter and try to verify, try to basically take our DFT calculation result very close to the experiment. But that is again phenomenological in nature. Then another disadvantage with DFT is that it neglects the van der Waals interaction, and there are other approximation that it ignores the polarization, and that is not also included in DFT personal. So possible solution would be that approximate the expression of dipole-dipole van der Waals interaction process on the basis of local projectivity derived from DFT. So in that way, what we can see that there are several things that is not being considered in simple DFT calculation, but there are some working model through which we can take all these things into account. So the next 10 minutes, I will just describe some of our work that we did using this DFT calculation, and that we used for a strongly correlated magnetic system that is spinel cobaltites. So the spinels have the general formula, which is given as AB2O4, and this is the pictorial diagram for the spinels. So in that case, we have the carbon which is sitting on the tetrahedral side, that is represented at A side, and the other carbon is sitting at the octahedral side that we represent here with the B side. So, so in that case, we did this work with Sandeep when he was PhD student in PhD department, along with Professor Subhash Thota. So here we discussed that if we dilute this spinel cobaltites with many of the magnetic and non-magnetic element, then what happens to its magnetic ordering? So here in this case, I just described this spinel structure, and dilution is done on both on A side as well as B side with the parameter X. So if we have the X equal to 0, then we get the normal spinel structure. But if we have the X equal to 1, then what we can see here on the tetrahedral side, we don't have any carbon. So that we are describing as an inverse spinel structure that we will be getting. And then we have the mixed spinel in which X lies between 0 to 1. So in this case, we basically analyze this effect of different element, an element which use germanium, aluminum, titanium, ruthenium, and tin, and we basically substitute the carbon in octahedral and in tetrahedral site with different elements. So here it is being substituted, this tetrahedral site has been substituted with germanium, here octahedral site is substituted with aluminum, titanium, ruthenium, and tin. So here we are showing the result based upon that which compound is stable in nature. So further, we perform the DFT calculation using the Vienna ab initio simulation package WASP, and we have used this DFT plus U scheme to take into account of the strong correlation between the electrons, because here we are dealing with the strongly correlated cobaltite system. And for that simulation, we have carried out by taking 8 cross 8 cross 8 K grid points in the Fourier space. And for self-consistency, we have used the converse criteria 10 power minus 7 electron volt. And structural relaxation has been done by computing the criteria that force is below 10 power minus 4 electron volt per angstrom. And for the exchange correlation, we have used local density approximation as well as generalized gradient approximation. And this is just the pictorial diagram that I already discussed. We are using in the WASP package. So with this, we get using this, we get the several result. And what we have done here, I mentioned that to take into account of the Coulombic interaction, we consider here the pre-parameter U. And that we have varied between 2 to 6 for the cobalt atoms. And for the dopants, because I told you that there is no particular theory which can tell us that what should be the value of U. So this is just being considered as like a working parameter. So depending upon the parameter at which we are getting very good the confirmation with the experimental value, or very good agreement with the experimental value, that value of U we generally consider. So here what we basically see that this cobalt oxide is in the AFM state, and when we substitute with the germanium, then again it is AFM state. But but there are some inverse panel that also we get it is in the AFM state. So so further we calculate the bond angle and bond length using this WASP software. And in next class, in next session, Sandeep will discuss this thing for some elementary metal as well as for this particular system in more detail. So what we get here, that if we use this DFT plus U, and this is the value obtained from the experiment, and what we can see that although we are using DFT, which is at temperature T, and we are dealing with the ground state energy, and our method is giving very good agreement with the experiment. So using that, we also calculated the density of states. And again, Sandeep will discuss more about that. So here, EG, 2G correspond to the crystal field splitting. And in the WASP basically gives two sort of density of states. So here the yellow the region basically denotes the total density of states. And this line denotes the energy density of states when we project the density of a state on a particular atom. And how to analyze this thing? One thing what we can see here that this zero is basically zero corresponds to the Fermi energy. So if there is no density of a state present in this region, so the band gap will be this one of the system. And then we can see that which orbital is localized at what energy value. Through that we can get an idea that what are the electronic configuration for that particular compound. So, so using that, we got this sort of configuration of the electronic states for these different sort of substitution. So we get this for cobalt oxide and cobalt aluminum oxide, S is 3/2. So it has this state. So we can say that we can see that it is in paramagnetic state, and then this one is antiparamagnetic. This is the antiparamagnetic ground state, and then we can get the ferrimagnetic ground state also. So with that we come to the conclusion that cobalt oxide and cobalt aluminum oxide has the antiferromagnetic in nature. Cobalt germanium oxide has AFM configuration. However, this cobalt titanium oxide and cobalt tin oxide, it has the ferrimagnetic in nature, that in A site we have the spin, the total spin that is lesser than the spin at the B side. So in that way, what we see that it gives us very nice the idea about the electronic state configuration, as well as its the magnetic the behavior of the system. And on that basis, again, we calculated in detail that what is the exchange parameter, this magnetic moment as well as exchange parameter at different sites. And through that, we also basically projected super exchange behavior for inverse panel copper titanium oxide. So, with that, we also got an idea about the direct band gap for different compound with different substitution. And here I am giving the picture that we are getting from the density functional theory. So this is the different symmetry points in the reciprocal space, and that basically gives us that what is the band gap present at different reciprocal points for different compounds. So, so the overall picture then we combine, and we get very beautiful this observation that as we increase the ionic radius of the dopant element, then this band gap basically decreases, and it gets exerted once we go for higher and higher element. And here we have shown that very good agreement between the experiment and the theoretical result. So with this, I just summarize my talk that in this talk we have given a very brief introduction of density functional theory, and we have mainly concentrated to describe the formalism for the ground state of the material. We have not discussed about the excited state. So another direction people can discuss about the excited state of the material. And in that context, we have discussed a different theory like mean field theory, Thomas Fermi, Hornberg-Sam theory, and Kohn-Sam formalism. And then we discuss some of the fundamental theory that can take into account of the exchange correlation like LDA and GGA. And Sandeep will discuss more about this DFT plus U calculation and that I introduced for the spinel compound. So with this, I want to thank my collaborator. First, Sandeep Ghosh for his very hard work, and because with Sandeep we started the work on DFT, and then I want to thank my collaborator Subhash Trota, Subhadeep Ghosh, and Sobi's team, and I also thanked this Paramisan, because when we started the work that time Paramisan was installed, and it helped us a lot to complete the things and get the good result. So with that, I thank you all, and we'll be happy to take the questions.
Thank you, Pankaj sir. I will take a few queries posted by the participants. The first one is that, is it possible to properly incorporate van der Waals interactions along with DFT through brain cycle? If so, how to determine parameter? It is not known for the system.
Hello, can you repeat your question?
Is it possible to properly incorporate van der Waals interaction along with DFT? If so, how to determine Green's parameter if it's not known?
So that I mentioned in that we can take into account of the dipole-dipole interaction, and in that case, we have that what kind of magnetic field present in the system. So accordingly, we can take into account of dipole. Just a minute, I just take a call, then I come. So, in that way, we have to take into account of the dipole-dipole interaction, and through that we can take into account of this van der Waals interaction. That is missing in the exchange correlation.
Next is that Much user-friendly GUI, free TFT software because for gas and water sensing applications.
Yeah, so for photo sensing application, we have used one software that Sandeep will discuss in more detail. We have so I think I leave it for Sandeep to basically discuss those things in more detail.
Thank you, sir. So the next one is that is it possible to use fast for transport calculation?
Yeah, people are using VAS for transport calculation, but I can see here that if we want to discuss about transport calculation, then we need to take it into account of the dynamics, and we have to take into account of the temperature. So there are some time what people do that people get this energy and density using the VASP, and then they use this they club this thing with molecular dynamic simulation and calculate the transport calculation.
Is it possible to use date for photoluminescence study?
Yeah. So it is possible to because you can see here that we are calculating this energy band gap, and that can be related with by studying some of the optical characteristics of the system. So again, Sandeep will discuss some part of that because I skipped most of the part that we have done in the paper, but Sandeep will discuss some part of it.
Possible to calculate animal conductivity by day.
Again, I mentioned this thing that because whenever we try to describe this, because the thermal conductivity, again, it will depend upon this transport behavioral system. So we need to then club this thing with molecular dynamic simulation in order to calculate this transport behavioral system.
Answering the queries. For taking time to join us for the event.
So VASP is not free software. VASP is the paid software, and here we basically pay around 3 to 4 lakhs for IPS.
Thank you, sir, for joining for the event. We'll move on to the next section. You can log out if you.
So thank you.
Yes, sir. Moving on to the demonstration session of the density functional theory calculation using VAS. For this, we welcome Dr. Shanti Ghosh from Changbuk National University from South Korea for leading this session. Dr. Shanti Ghosh is currently working as a postdoctoral researcher in the Department of Environmental Engineering, Changbuk National University, Republic of Korea. He received his PhD degree from Department of Physics in the Indian Institute of Technology, Guwahati in 2021. Then he joined as postdoctoral researcher in the Department of Physics, Changnam National University and Kunshan National University, Republic of Korea from April 2022 to November 2023. His research interest include studying nature of electronic correlation in different archetypical strongly correlated materials within density function theory. His research work focuses on computational correlated material design with desired physical properties based on basic understanding of the electronic correlations. If you are available, it is over to you, sir. Chandip, sir, are you there?
Can you hear me?
Yes, sir.
Yes. Okay. Thank you for the introduction, and thank you for the organizing committee for giving me the opportunity to express my work and what I have done. So I will give a a brief idea how this density functional theory works using WASP, and the introduction which Pankaj sir has already given, which will help me to carry forward. So I will just share my slide once. Mm, Can you see my slide?
Yes, sir.
Okay. So in this talk, what I will be mainly focusing on that the theory what Pankaj sir already discussed. I will try to club up all these things and try to explain how this theory works using a package. Basically, I will mainly focus on WASP, that is Vienna Ab Initio Simulation Package. So there are multiple quantum chemistry codes if one consider. So there are Quantum Espresso, which is very popular because this is free software, and there are other Sista, Wine2K, Gaussian, WASP. So mainly I worked on Vienna WASP and Quantum Espresso till now. So I am much familiar with these two codes. So I prefer to choose with the WASP to explain what happens. So before I move on, I just want to explain. I just want to mention that. I just want to mention that you can use any of these packages. It's not a problem because it is already mentioned earlier in a paper that all these packages gives the same type of results. But the main difference between all these packages is the pseudo potential that Pankaj sir already mentioned. The pseudo potential is prepared differently for all, not differently, it is different for all the packages, and that is the main difference between all these packages. Mainly the WASP is widely used, but it is commercial. So anyone have to buy, I mean, institute have to buy, and after that you can use that package. But Quantum Espresso is a free package. You can install and run it. So there are all good amount of means materials are already in the internet. So you can get access to any of these things. So before moving on, I just want to mention that if the WASP is the, what is the main important of this WASP, that it is a very well documented, and you can get the WASP document in the link which I have shared. And if any problem occurs, you can easily go to this PDF file and you can search anything which is relevant to you. And it is a very good documented thing. So I am mentioning many times this thing because it helps me till now also while doing anything till now. I used to go to the vast manual, and it is very helpful. And what is the other packages which are much more important, that for the post processing means we will run this WASP and we will get some output. But how to get this post processing, how to get this output data to be plotted and published in a paper. So for that reason, we generally use this WASP kit or P4 WASP or XCrisDen, Vesta, anything. So hopefully these are known to many people. And there are two other domains also, the material, project, and moment. I will show everything which is possible in this limited time, and hopefully it will help you. So basically in WASP there are many input files and output files also. So I have listed down the all the input files and output files. Before moving on, just want to say that this is will take a little bit time to familiar with these input files, but just try to remember that there are four important input file which I have double star here with the in-car, pot-car, k-points, and the post-car. So what is this in-car file? In-car file is the central input file of WASP, which where we determine what to do, how to do, and what are the things. We use different types of tags, and all these tags, there are a huge number of tags. So basically I will mention few tags which will help to run this WASP at the initial period of your research. Later on you can move on to different tags and try different flags which will be helpful for your materials. So this input here, we give different parameters and we just ask the package to run how we want. So basically what we WASP is well coded system. where we give some inputs and we will get some outputs. So we have to use certain parameters from where he will understand you want to do this simulation, you want to do this type of simulations. So basically this is a input parameters, a huge number of input parameters which we give in the in-car file. The podcast file is the pseudo potential file, which I mentioned that it is different for our different packages. And for Quantum Expresso, it is free, but for the WASP, again, you have to buy it. And hopefully Institute will help you in this case. And the K points are the mesh or the grid which we will be using. So this is the, suppose we are, since the materials have a huge number of atoms, but we can't put all, suppose we have 200 atoms. So basically putting a 200 atoms and doing the simulation is very difficult. So what we do, we prepare a primitive cell and just do the periodicity. So suppose we have one primitive cell with 14 atoms and we will do the periodicity by increasing the value of the K points. Suppose if we have 14, then we have 2 cross 2 cross 2. So it will be multiplied by 14 into 2 cross 2 cross 2. So this number of atoms will be doing. So due to the periodicity, it will be work much more quickly. And the Pascal file is the informations which we use to provide for the lattice parameters and the positions of the atoms. So these four are the basic input files to run a WASP in any terminal. So now moving on to these input files, here I have tabulated very few parameters which I will be I am showing right now, and later on I will run this to show how it runs. So just try to take it as remember what I am using the tags, and I will use these tags later on to run this MGO system only. So here I have mentioned the system. Here you can write the system name MGO, which I will be demonstrating today. Here which I start can be having this default values 0 and 1. For 0 it will be the initial start, and for 1 it will take some input file from the earlier data, which I will also mention. Here this I charge the charge density. So what type of charge density you want to mention, means what type of charge density you want to use, that we want to mention. So here is possibility of 0, 1, 2 again. So if any thing is not able to remember, then you can go to this WASP wiki and you can type any of these parameters and it will be come out what this parameter is linked to. And here first I will go to this N card. So what is this N card? This is the energy card. Since we are talking about the pseudo potential, means in the pseudo potentials we is the effective potential which we construct from all the atoms. So basically we neglect the core electrons and we take only the valence electrons to prepare these pseudo potential files. So we have to give some N cut from where we will not consider the core electrons and we will consider only the valence electrons. So basically in this N cut we use the N maximum which is in the podcast file again. So I will show that. So how to get this value of N max, and I have mentioned that it should be higher than 1.3 times larger than this En max which is in the podcast file. So basically in our case the oxygen have nearly 400 electron volt, and for Mg I remember it is 250 electron volt. The En max. So basically, so I have used the N card much larger than 400. It is nearly 1.6 times of this oxygen. So I am using this En card, and there are two other steps, that is NELM and NEL min. So what are these two steps? Basically, it's not necessary to play with these two parameters. It is not required because in default the NEL min is nearly 2, and for this is nearly 60. But I just showed you that you can tune this one, but this is not so much necessary in this case. You can use the default values which is already there. And another thing I just want to mention, if you don't put any values like this, there are some default values are already set. So basically you have to give some parameters and automatically it will take the default values and it will start doing the iteration process. So if suppose if you don't choose these two parameters, you don't use these two parameters, then it will take automatically this element will be 2 and this lm will be 60, which is the default values. So the default values are already set for this different tags. So it is we need just to change this tags value according to our system. So I generally don't play with these two parameters. For showing these things, I have mentioned these two. And now moving on to this, sorry, this will be edef e. So it is, so edef e is this energy difference between this, where the convergence criteria means we have to, since this is a iteration process, what it takes that, as Pankaj sir mentioned, that it will iterate and come to a ground state row. So there we have to give some convergence criteria. So the convergence criteria is this is EDIF, that is the convergence criteria of the energy. So it will be the when the energy difference between these two steps will be 10 of the order 10 to the minus 7, then it will the iteration will stop, because we have to give some convergence criteria when we want to stop the calculation. So this is very important. So here I have used 10 to the minus 7. And there is another tag which I have mentioned, eye smear. So eye smear is different types of smearing process. That can be Gaussian smearing, that is the Fermi smearing, that is the MP smearing, anything. So here n is equals to 0 is the smearing process, and sigma is the deviation, that is we are using 0.02. So basically this sigma as eye smear, if you go to this VASP wiki, then you can get the default values also. So now moving on to the ionic relaxation. So earlier, which I was mentioning, this is the electronic relaxation. Means between this electronic step to electronic step, what will be the energy difference? And what is the ionic relaxation? That since we have the cell, now suppose we consider any material, but we don't know what is the exact lattice parameters or the atom's atomic position. So what we do, we basically relax the system. So how we relax the system, there are different process. So here I have mentioned all the different values of Ibrion. So basically I am using Ibrion 2, that is the conjugate gradient algorithm. I am not going to these details because it will take much time to explain what is this algorithm, but we are using this Ibrion 2, which is mostly used for this material relaxation. However, for Ibrion 3 is used for the molecular dynamic studies. And here which type of Ibrion means which type of method we are developing is important to mention. And the second thing, there is IC. This IC is equals to 3. So what is the meaning of 3? This is that it will calculate the force, stress tensor, position, cell size, cell volume. If we use this IC2, then the cell shape and the cell volume will be same. The cell size which we will provide, it will not change. The lattice parameter will not change. It will remain the same. And if we give a crystal structure like a cubic one, then it will remain the cubic structure. Although your structure changes to some orthorhombic or monoclinic, but it will not change. So basically these tags are very important for the relaxation process. So here I have mentioned IC3. So it means that if this MGO, if the initial pause curve which I am providing is cubic in nature, and it may go to some structural transition can take place, and it can go to some orthorhombic or monoclinic, then automatically the cell shape will change. The atoms will be allowed to move around some positions and where it will relax completely. Now, what is the meaning of relaxed, which I want to mention? That is the thing, that what is the ground state of the energy. So basically every system has a ground state energy, and when the system is completely not relaxed, then the ground state energy which we will be getting is much higher. And due to this higher energy, the system is the different properties which you will try to evaluate will not come properly, will not give the accurate results. So the relaxation is a very important process in these things. And another two different tags, that is the NSW, that is that how many ionic step I want to do. Earlier was the electronic step, which I have mentioned here, that Nelim and NELM, and this is NSW, that how many ionic relaxation you want. So here also I am using 99. It is too high for this kind of small systems MGO, but I have only showing these values. When you are going to a large number of atoms, we have to play with this NSW, ISAP, IBRION, and you have to go much closer to the experimental results, means the lattice parameters or the weak up positions of different atoms which are in your system. So these things are important, and EDIFG is the force criteria, because here we have written that ionic relaxation, there are two different types of loop. One is the electronic loop and another is the ionic loop. So basically when we will get out from this ionic, because after the electronic loop there will be one ionic loop. So when we will get out from this ionic loop, that is given by the force that is in the of the electron volt per Armstrong unit. So these are the input parameters which are very important. There are plenty others. So according to your systems, you have to choose these input parameters. These are the most important which I figured out till now. So now moving on to the POSCAR file. So what is this POSCAR file? As I mentioned, POSCAR files contains the information of this uh, of the positions of these atoms. So basically, if I see this, which I have taken the screenshot, this is the command line which atom you are using. So I am using MgO. So and this is the universal scaling factor, which I have used 1. And if I have don't, and I have written nearly 4.2 Armstrong. So this is a cubic lattice. So basically, so the Bravais lattice vector looks like this, where we have only A, B, and C equal to, all are equal to each other. So if it is an orthorhombic or structure, then it will be something A and C will be not equal to each other, and A and B will be equal to each other. So like that, depending upon your system, you have to choose the Bravais lattice. And now these are the I am using 8 atoms. So basically I have mentioned 4 Mg and 4 oxygen. So these are the positions of the 4 Mg and these are the positions of the 4 oxygens. So you have to mention these things properly. And another thing, that here you can use the Cartesian coordinate or direct or fractional coordinate. Here I have used the fractional coordinate, but if you want to use the Cartesian coordinate, then you have to multiply your positions with the lattice parameters, and then you have to write here. So basically for this scenario, for the A, you have to multiply with these things and we have to get the positions, and you have to tabulate for the Cartesian coordinate. So now moving on to this podcast, where podcasts are all the pseudo-potential files and where we get from VASP. And commonly we have these pseudo-potential files individually. Suppose for Mg we have a pseudo-potential, for oxygen we have a pseudo-potential. But since I am mentioned for MgO, so we have two different elements. So we have to club these two different podcasts to a single podcast. And the comment for that is cat. And once you do that, then you will able to see the both the podcast together. And so, and now moving on to these K points. So here I am using, there are two types of grid, gamma grid and Moncross grid. So here I am using Moncross grid, which are generally used for this solid materials, but for the gas we generally use for the gamma pack. And here I am using this 8 cross 8 cross 8. So basically my primitive cell is multiplied by 8 in all the 3 directions. So in A we have 8 primitive cells, on B we have 8, and on C we have 8 primitive cells. And finally there is a script file which is required to run for the VASP. So so that you will get from anywhere you are using supercomputer, hopefully you will be using, and you will be getting, or any cluster which you will be using. So they, every clusters have the, according to their environment, have their different script files. So this script file you have to obtain from where you are running or submitting these jobs. So now, as I mentioned at the initial slide, I have shown you there are multiple output files, but to discuss all these output files will take much time. So I have listed only 3 output files which are important for right now. So the outcar files is a file where we everything contains, means it contains all the information of this output when you submit a job in WASP. So it will have the input parameters, also it will have the consum eigenvalues, stress tensors, force, magnetic moment, everything will be written in this outcar. And you can tune this what you want to write in this outcar with nwrite tag, but I think it is not quite necessary to play with this one, because all the information in one file will be helpful for when something you are looking back much, so it will be much helpful. So but if you want to don't write some certain, suppose you don't want to write this dielectric properties in your outcar files, so you can tune with this nwrite tag. So there are many options for this nwrites, and if you choose certain integer of this value of this nwrite, then it will automatically give you the output accordingly. And for the Oziker file is why important, that I will come when I will show, I will give a demo of this MGO. And what is this concar file? This concar file is the, suppose we are relaxing a structure. So first we give a postcard, and this postcard will relax, and you will certain get a new positions and the lattice parameters of this structure. So basically what will happen, it will move from one position to different positions. So the new positions will be saved in this concar file. So you will start with a postcard, but the new positions will be listed in the concar. So these are the important things which are required to run WASP. So here in this tutorial, I will focus on two calculations. I will show two calculations how to do. One is the density of states calculations and the band structure calculations. So how to do these calculations? First, I have mentioned there are only four input files. So these are the input in-car files for the relaxation one, and this is the SCF one. So what is this SCF? This is single point calculation. Means in this case, the iteration will not take place. Only the electronic calculation will be done, and it will be finished. There will be, suppose you have given a particular value of rho, and you want to do the calculation for that particular value of rho. You don't want to change this value of rho after each iteration. So this is a single point iteration. So you just want to fix for a certain value of rho, you want to see what is the charge density or what is happening. So for that we do the SCF calculation. Means basically we generate the final charge curve file, which is important to calculate for DOS and the band structure calculations. So first we will do the relaxation. And what is the what are the important tags which are different? Here you can see we have not used this L charge, means the charge card file, where the charge card file means the charge density of this system is not written. But here in the SCF calculation, we want to generate this charge card file. So the difference is, with this charge card file, I have mentioned true. So I want to generate this charge card file. And second, since I mentioned that the relaxation of the ions are not relevant to this one, because we are doing a single point, we already get the concar file. So we get the relaxed structure, and according to this relaxed structure, we want to generate the charge density. So basically, we will copy this concar file from the structure relaxation to this SCF folder, and we will generate this charge density, which charge density is useful for calculating the DOS and the band structure calculations. The other postcard and K points remain same. So for the density of states calculation, again, what I need to do, that I need to, since I mentioned here that I will take this charge curve file. So basically, you can see the change which I have mentioned here from iCharge 2 to iCharge 11. iCharge 11 means it will read the charge curve file which is already in the folder. So it will not generate any charge curve file charge density randomly depending upon the atom position. We already generated the charge density of the system, which we get the ground state as rho naught, and for that rho naught we have the we have the charge densities, and we will use that particular charge density to calculate these DOS and band structures. And here I have mentioned that here is I start 0. It was 0, but here I am using 1, means it will read the charge card. If I put 0, then there will be a error that since I am using this 11 and this is 0, it will not able to calculate anything, because it will be confused. Again, if it is 0 means it is a initial run, and I am telling to read the charge curve file, so it will get confused and it will come the error. For DOS, we use generally ISMEAL 5, and to decompose, because we have many orbitals in these different materials. Sorry, not S, P, we have PX, PY, PZ, and for D we have 5 orbitals: dx, y, dy, z, dzx, dx square minus y square, dz square. So when we write this L orbit 11, means it will decompose my density of states. Suppose we have the total magnesium and oxygen, and in magnesium we have px, py, pz. Oxygen we have px, py, pz. So basically it will decompose my density of state corresponding to this px, py, pz, and this is the L orbit which 11 helps to do that, to decompose our density of states. And any dose is that number of density of states you required in the interval. Suppose I am calculating, I have given an interval, suppose 0.1 to 0.5. So in this interval, I need 2000 density of states. So basically you can fix that interval, and you can use number of density of states you require between that interval. So that is 2000 in this calculation. And what we do for the DOS calculation, to get a better DOS, we generally increase the K points, which was not for this. We have used initially 8 cross 8 cross 8, but here we will increase to 12 cross 12 cross 12. So basically what we will copy this cont card and pos card to this DOS folder, and we will copy this charge card, and we will again perform the calculations, and we will get the density of states. Now how to post process this density of state, that I will show you by demonstrating everything. So I'm just going on what I will be doing till now, and this I will explain later when I will finish the density of states calculation. I will explain this later. Just to mention you that these procar and doscar are the important files for the density of states calculations. And here for the procar, which I mentioned, I have used L orbit 11. You can see it is decomposed in S, P, y, pz, px, dxy, dyz, dz square. This is decomposed. And similarly, this is for band 1, this is for band 2, this is for band 3. So here we can see what is the important of this L orbit, and this is the DOSCAR file. So we can fix this Emax and E minima by mentioning in this input files. You can write here Emin and Emax. Then here I didn't mention, so it has to automatically from 30.6 to minus 16.2. If you want to fix it, then you can write that here Emax 5 and E minimum minus 5. Then the density of states which you will be getting is between 5 to minus 5. And this is the Fermi energy of the system, and which is required for the plotting. And this is the 2000 which I mentioned, that is the any DOS, that it will have 2000 values between each energy intervals. And in the DOSCAR files, I will show you that there are the so this is corresponding to a band, but this is corresponding to one energy here, which we can see that it has been written in this manner, where this the first column is the energy. This is for the s orbital, this is the 3 p orbitals, and this is the 5 d orbitals. So it is also listed in DOS card also. So the thing happens that here you can see you have ion 1, 2, 3, 4, 5, 6, 7, 8. So getting out one, extracting this data by writing a code is very difficult. So manually it is very hard. So you can extract the data manually from DOS card. So here we have along one energy range. So this energy range we have all these values. Uh, so this again I will show you, and I will come these slides again to how to use these different post-processing software. So we will be using two software to show you. One is P4 WASP and another is WASP Kit. So both are very helpful to plot this density of states data, and how to plot it I will show you right now. And another, before going to the demonstration, I just want to say about the band structure calculations, and it is quite similar to the DOS, but the thing main difference is the K point. The K point, if you can see now, the I have mentioned there are along the reciprocal, this is symmetry points. This is not the K mesh. So the band dispersion generally shows along a certain path. So you should know along which path you want to see the band dispersions. And this is the path which I have choose for MGO. And again, the question arises how to get this band paths. What is the symmetry points of the system? How to get this one? So these are all you will get. I will show how to get it, but this is already there are different software to get the symmetry point of any system. So, and the main difference between the earlier incur file of DOS and in the band structure is here we change the isomere to 0. So here we did the isomere 5, which is the Fermi distribution, but here we have we are using 0, that is the Gaussian smearing. Remaining everything is quite same to the DOS calculations. So here is I have shown that which I have how I have generated this K path. So there is a tool WASP kit. So it is freely available and it is very helpful to do post processing or prepare any input file. It is very helpful. So basically here how to install it. So you can type in Google the WASP kit and you will get the link of this software. You can download it and install in any Linux system. Yes, but it is not user friendly to the Windows one. It is for the Linux systems. So basically here I have chosen the 3 for the K band structure, then the bulk structure, since we are using the bulk structure, and according to the postcard files, because I have already given the primitive cell, they will generate this code is already processed to generate according the postcard file, and it will give you the high symmetry points along which the postcard file which I have given, and you can use these high symmetry points to do the band structure calculations. So again, I have used the P4 WASP to do the band plotting, and I will show in much more details. So before I go, I just want to demonstrate that will help you to understand. So hopefully you can see my console right now. Uh, can everyone see my console?
Yes, sir.
Okay. Okay. So here basically to run, which I have mentioned, we will do DOS and band structure calculation. So before doing that, we need to relax our system. That is the relax. So I have prepared a folder named relax. So what the 4 input files we required: in-car, K points, postcard. Podcast is not here, so I have to prepare that podcast, and this is the script file where I will be running my code. So this is a script file. So it will, depending upon the which module is there, which VASP is installed, so it will change accordingly. So according to the environment, we have to change that. And this is a very simple command: mpi run wasp stand dot out. So this is the comment from where, means if I don't write this script, I have to enter this 3 lines every time. So basically, once I run this script, it will automatically take this 3 line continuously and it will start running. So first, that is the script file. Now moving on to this postcard file, which I have shown earlier. So this is for MGO, and this is for the lattice parameters. So basically, let me change these lattice parameters to 3. So see that whether it relaxes to some position or not. So I will change it to 3. I have increased I have increased the lattice parameter, nothing else. So it was 4.19 before, so it was the relaxed structure, which is 4.19. So I have increased whether see we can go to 4.19 or not. So this is the K points, and this is the in-car, which I have mentioned in the earlier slides. So this is the in-car, which are the parameters which I am using here. And again, before now, just I remember that I have this potential files in this folder pot pay pbe. So here you have all the potentials of any elements. So you have to get this from after, you will get this after you buy after from WASP. It is not available freely in internet. So now relax. So now I mentioned I will use the comment cat. So now this is mg. As I mentioned, I am doing this podcast mg and pot bay oxygen podcast and podcast. So this is the comment, and if I do this, then you can see there is a file generated podcast. First, I mentioned that EN max should be higher than these two different podcasts. So let's move on to that and check what is this EN max. So first check whether we have these two podcast or not. So we are HFIN. So here you can see it is for MG, and here you can see it is for O. So both the podcast has been written. So this is MG, this is O. So this is correct. So now moving on to this podcast, which I mentioned that what is the EN max. So EN max. So this is 400 for oxygen. This is 200 for magnesium. So basically I am using 650. So it is much larger than the oxygen. So it will not cause any problem. So I have in-car, K points, postcard, podcast, run. So now I will just queue sub. This is the command to run the script, and it will start running. So it is running, you can see. And if you want to see, so it already run. It is completed, and after 4 steps, it has been reached to the convergence criteria which we have set. So let's move on to this Aussie file, which I mentioned. So this is the number of steps you are doing in one electronic step. So these are the electronic steps. This is one electronic step. This is second electronic step, third, fourth. And I said that 10 to the minus 7 will bring out from that loop. So here you can see after 10 to the minus 7, it is bringing out from that loop. So 10 to the minus 7, 10 to the minus 7. Again 10 to the minus 7, this is 10 to the minus 7. So this is DE, which is the energy difference between these two electronic steps. And this DE is the energy difference between these two different steps. This is between, this is suppose 2 minus 1, this is 3 minus 2. So like that, this is the energy difference. So now where this ionic energy comes, now I have given the ionic, I have said the EDIF G, yes. So where to check that one? So if I go there, so I can see that this is the force. So I told that this is the energy difference which will come, and the force will converge to 10 to the minus 4 Armstrong electron volt per Armstrong. So here we can see the our force is completely zero. So it is also convergence our criteria. So that's why it is completed. Now another thing, this is the total energy of the system which you will get for MgO. Our total energy of the system means our 8 atoms we have. For 8 atoms, and the MgO have the energy of minus 47.67. And lastly, I will see this concar. See now the postcard which I have given was 30. So now I have given the count card to check. So the relaxed one goes to 2.44. So earlier was 119 was just I have changed that. Hopefully I forgot that. So 4 point. Now what we can do, we can check whether this is the correct one, whether the more precision is needed or not. So we can first copy this count card to the postcard. So now my count card and postcard are same. Now again I will run this one to check to see anything is changing or not. Again it has been run. No, it is running. So this is the first loop completed. And after that, since I have used the same the same count card, so basically it is not taking any relaxation is not happening, and you can see now the present count card is same, so there is no change. So the lattice parameter has been reduced, which we can see, and this is our relaxed structure. If you want to see this relaxed structure, you can easily use this Vesta software, which is again freely available. There are many visualization software. So basically you can just transfer this count file or postcard file, and you can see that whether your structure is remaining same or not. So I just copied it here, and this is our count card. So this is again the cubic symmetry, and this is the magnesium oxide, which is same, means the cubic symmetry is the same, and this system mainly is cubic in nature. So now moving on, so once the relaxation is done, we will move to this SCF calculation. So what we will do, as I mentioned, we have to copy this count card, means we have to copy this count card to this SCF. So I will copy from the relax and count card. But the thing is, if I use count card, it will not be able to read. There will show some error. So I can show you that error. So since I mentioned it should be postcard, not count card. So if I run, it should not run. Let's check. Okay. So there is the error which is showing the following file does not exit postcard. So I refuse to continue with this sick job. So basically we have to then we have to move this count card to this postcard because we don't have any postcard. Now we run this job. It is done already. If I can show you, so that error message has completely vanished. And if we go down, then basically all the informations in the outcard, I mentioned that everything will be mentioned here. So it will be a larger file which contains all the information of this output. And you can see that after one iteration, iteration 19, iteration 110, 111. So this is the iteration process. This is the K bands which they have calculated. And like this way, we will get the total energy and again the free energy, and this is the output. When this comes, generally the job has been run completed. So the thing which is new that L charge, which we have mentioned, and we have opt out this since we are doing a single point calculation. So ionic relaxation is not required. Only electronic criteria is required. So we have removed all the ionic relaxations. So now, as I mentioned that we have generated a charge card. So this is the charge card. So this is the POS card, means which we have inputted, and this is the values of different charge densities for corresponding to different atoms, and it is a big file. If you see, the file size is quite big. This one is the charge card file. So now this is the up till this SCF has been run. So what we required to do the DOS. So first moving on to this DOS. So again we will check this in car. We have to set I start 1, I charge 11, and I smear -5. So we have did that, and we want to decompose the orbital contribution. So it is L orbit 11 and any DOS 20 to 2000. So again we have in car, we have increased the KMS, and now we will copy this SCF and the charge car file from this SCF. So we have 1, 2, 3. We will again copy the relax. We will copy this cont car, pos car 1, 2, 3, 4, 5. We are missing one file, that is the pot car file we are missing. Okay, so while doing this DOS and band structure, there is another input file, that is charge car file. We have to give it here, since we have we want to read the charge car which is generated from the relax structure. So now what I will do, I will just run this. Again, it start running, and it is running right now. So you can see, so after 7 steps, it has been converged. You can see it into -7. So it has been converged. So just so now there are two ways to extract the data. So now before going that, I will show you the manual way, which I used to do in my PhD also. So this is the total density of states. So here we have 2000 density of states. So basically, if you can see here, so this is 7. So basically 2000 means 2007. So see there, after 2000 steps, we have total 2000 density of states. So after this 2000 density of states, we can see there are partial density of states or projected density of states, because we are using L orbit. And this L orbit, this is the energy, this is S 3p 3p 1 2 3 4 5 5d orbitals are decomposed. So this is, now we have 8 atoms. So basically it will generate 8 different atoms corresponding to this density of state. So this is first Mg. So now, since this 2008, so our next one will be 4008. Okay, so this is the second one. Again 6008. So this is the third one. Like this, you will get the density of states for each atoms, and you can extract that by writing any code that from this line to this line it will be saved to some another data file, and you can plot it using Origin or XMGrace or any tool which you are familiar with. So this is the harder way. So now going to the simpler way. So, and again, yes, I forgot to show the pro card. So this is the pro card. This is the how many bands we have. We total have 30 bands. So corresponding to each bands, we will have band 1 to band 30. So if we go band 30, so there are 30 bands, and corresponding to each band, each atoms are there. So which band is in which band, which atom is contributing and which orbital is contributing is significant to see. So suppose this is I am talking about this 30 band, and you can see this one was, this 4 was Mg and this 4 was oxygen, and you can clearly, we clearly know that this Mg and oxygen does not have these d orbitals, and you can see the contribution from the d orbitals is 0. So it is all in, we can understand what is happening, why it is 0. So like this, we can have the procar. Again, from procar also you can extract the data, but it is a very hard task. Means not a hard task. You once you have to write a code, and corresponding to that code, that data will be generated. So now first I will show you using this. Uh, so this file is very important, vast_run.xml. So what I will do, I will copy this vast_run.xml. I have copied to my system, and I already installed this P4 WASP. This is a helpful tool post process which will help you to post processing your data. So what we will do, we will just open this P4 WASP. I'm sorry, it is taking a little bit time. So just I will open it. I am in the desktop. I have this vast run XML. So I have opened it, and as I showed here, plotting DOS. So I have opened it, and I have choose the fast file. I have clicked OK. Now I will click on DOS. So I will click on this. So you will get the density of states. So it's reduce your job, means it is very easy. So you don't have to extract any data. So this is the total density of states which you will get. And now after that, here I have shown the control of different orbitals. Here I have shown the different orbital contribution. So let's see how to do that. So I have this DOS. Now I will go to this electron local band control. So what I want to see, the Mg I want to see. So this is the p orbital I want to see, and I will select only the p. I don't need, I will not select individually. I am selecting, it will add all the p together and give you some line. So it is happening, data is processing, and you can see clearly the p lines here in the below. So the contribution of this mgp orbital. So now again you want to see, okay, so we got the p1. So let's see the oxygen p. So it is already choose. So I will add new line. Okay, so you can see clearly the oxygen is the much more contribution in this MgO compound, and you can see that since another thing which I forgot to mention, we have shifted in this P4 WASP. They generally subtract the Fermi energy which I mentioned. So if I go to this DOSCAR, the Fermi energy. So this is already subtracted from the DOS density of states file. If you want to collect from this DOSCAR file, then you have to subtract this value from each energy to shift your Fermi energy to 0. But for this package, it already reads the Fermi energy from this DOSCAR file, and it subtract the DOSCAR file, and it will give you a nice plot. So here we can see the contribution of oxygen 2p is much larger than the magnesium p. And now this is not a good way to represent in a paper. So basically here are many options to export the data. So just go there, export the raw data, or you can choose the AGR data or anything you can wish. So AGR data means the XMGRACE one, or you can use this EPS PostScript file or EPS file, what you require you can choose, and just save the file. So if you want to decorate much more proper way, so just generate the data file, that file, and you can plot which software you are useful or you are handy with, you can use that one. So this was the density of states. how to plot the density of states, so which we have done. Now this I have shown using P4 VASP. But there is another thing which I mentioned, that is the VASP kit. So the VASP kit is already installed in my console. So I will just type VASP, and the VASP kit has many things to do. You can see you can calculate transport properties, magnetic properties, charge density analysis, Fermi surface analysis, many things you can do. So right now we are sticking with the density of states, which is required for our case. So basically we will generate this here 11. So we have to put this 11, and here we have different options. That is total density of state, projected density of state for each selected one atom. This is each element. This is selected atom. So there are many means there are nearly 10 options. So I will go with this 113, which is density, project density of state of each elements. So everything is done, the data is processed. So these two files are important for me. And again, here also the Fermi energy is subtracted when the data file. So it is not a problem. So I will just copy this to post here. And we have this two one. So now, since I believe everyone is familiar with this origin, so I will open an origin file. So this is mg, and I have again another one, oxygen. And if you see this mg, this is energy, this is a total, and this is sp. You can see all the orbitals. So anything you want to plot, you can plot. It's not a problem. So this is total, means this is total contribution of mg. So it will show like this mg. Now, if you want to see the total contribution of oxygen, so plot setup, oxygen, twin, add, apply. Okay. So this is my oxygen. This is my mg. Okay. So now let's so much. Okay, so you can see clearly that the oxygen has the much contribution with respect to this mg1, and you can clearly see this is the gap which we are getting. But how to get the exact band gap, we will do for the band structure calculation, but the system is not metallic, it is insulator, and we know MgO is white semiconductor which shows nearly band gap around 6 or 7. So but it is not showing 6 or 7, so I will come that later why it is not showing like that. But you are getting a result which is a semiconductor image. And if you want to plot the contribution of any of these orbitals, you can happily do that. So this is the px, py, pz have the same contribution, so it does not differ in this case. So it does not make any sense. Again, for oxygen also, I believe it will be the same. So it is quite obvious why it is coming same. And this is how for the materials which you are working, if the orbitals have different contribution of the pxy, pz and px, so you can plot like that way and see which orbital is contributing in which energy range, and it will help you to analyze the data much better way. So now moving on to the band structure calculation. So this is the DOS which we have done. Now band. So again we have this in-car. Now again I have mentioned that this for the bands we have to give the k path. So how to generate this k path? We can, this is one way how we can generate. There are another software also you can generate the k-means by giving particular point at which point you want this path to go. You can choose the point by on your hand, so it's not a problem. So here the 3, which is the k path of band structure, and 303 is the bulk structure. Okay, sorry. So why it was unable to do? Because it does not have the POSCA. So I have to copy this POSCA. It will read along the primitive cell. Okay. So now wasgate 3303. Okay, there is showing some error. Let me check. Okay, the k path is given. K path dot in. Okay, yes, this is just generated. There is some error that can be ignored. That it is for the postcard file, so we can ignore. So this is the k path which they have given, and they have the high symmetry points. Like this, you will get the high symmetry points, and they have chosen this k path accordingly. So I have used this high symmetry point to generate these k points already, and I have prepared this k points path. And what I need this to copy the charge card file, which is not there. Is not there. The error why it's shown. The pot car file is not there. So I have all the things. So let me check the in-car ones. Okay. Now I will run. So it is running. I can check. So it is running, and there are 4 iterations, 5. So after we reach the convergence criteria, it will come out, and the convergence criteria is 10 to the minus 7. So it already came out. So till now, we have this VASRON XML. This is again, we can do using this P4 VASP. So I will just remove the earlier one for the confusion. So I will just copy this VASRON XML. Okay. So now again, we have to open this P4 VASP. Now we will open this. We have this VASRON XML. So first we have to click on this DOS or bands what we have. Then we have to go, because I have shown here. Oh, I have not shown that. Okay, so first we will choose this VASRON. Then we have to choose from show to bands. So after we first initially it will show the density of states, but this is not the correct, because this is not along this K mesh. This is along the symmetry points. And when we do, we will get this band structure. So we have this one. So we already have this one, and we will go to bands. And we have a good band structure, which is quite nice to see. And the thing is, where we can see the band gap is coming nearly 4 electron volt, greater than 4 electron volt. But in MGO, it is nearly 7 electron volt. So why it is the problem, that I will move on, that I will mention in my coming slides. So this is the band structure. And again, if you want to control the bands, you can just go to this control and this MG. So we have the oxygen much more. So basically we can see the oxygen contribution much more. So we will see the contribution of the oxygen and add new line. And you can see the contribution of the oxygen, which is in the red bubbles. So this is the contribution of the oxygens in this band structure. So like this way you will get that. And you can do one-to-one analog, because if we can see here that where is the oxygen? So oxygen was lying close to 4. This is so this was around -5. So this is a band which it is getting. So wait just a minute. So means basically, sorry. So I will come to the analysis a little bit later. Just let me proceed this one. So this is the band structure, and I have shown how to get that. And again, you can get this band structure by using this WASP kit. And 21 is the band structure. Now you want the projected bands. So you have these projected bands in the name of P band MG, P band O, and you can use these bands to plot in the origin, which I have shown earlier. So this is up till now the DOS and band structure plots which we can do. Now just moving on, that why the system is showing here. I have given reference, so it is showing nearly 4 electron volt, but correctly it is to the 7 electron volt. So but if we see the bands much more properly, then we can see this is along the gamma point. So this is also uh, this is along the gamma points and the K point. So we can see the difference. This is the gamma point. This is the gamma point. So it is nearly lying around 4. This blue one is the DFT calculations in this paper they have mentioned. And this is our DFT calculations, which is in line with the paper which they have already reported. The others are DFT plus U and DFT plus U plus V calculations, which I have not mentioned and which I will be unable to show because it will take much longer time to do the calculations. But I can say that the DFT results which they have obtained is in line with our calculations, because this is the gamma point and we can see the gamma point is lying in the same, and if we see the X point or anything which is closely matching to our calculations, so this is perfectly okay. So now here I'm showing in a comparison which I did while doing this DFT plus U plus V, and we can see that this was done using quantum espresso. The V parameter can't be incorporated in WASP. It is able to incorporate this in quantum espresso. And what is this U and what is this V, that I will come. I will explain a little bit later. So this U is the on-site and the V is the inter-site interactions. So basically when we use the strongly correlated systems, the spins are localized in one area, and in the DFT the localization is not considered, and that's why the DFT underestimate the band gap of these systems. Similar for zinc oxide, we can see that there is an underestimated because this is the correct band gap. But for the blue one, which is the PB, is having a band gap, they have reported 3.5, but our calculation shows it is nearly 3.3. It is nearly matching. So it is also underestimated, though we are getting a band gap, but it is underestimated. So this why this UNV is important to, since as Pankaj has already mentioned that this is the limitation of the DFT. So we have to consider this U and V parameters of the elements which are strongly correlated. But in this system, this magnesium one can say is not strongly correlated. So how come we need to consider? But this is the scenario that we have to consider. We don't have the d orbitals, but you have to consider the U for the p orbitals you can consider. So for, because of the magnesium and the oxygen, so you have to consider the for the p orbitals. So like this way you have to tune this u parameter and or U and V parameter. So I am leaving this V parameter right now because V is not available in WASP, it is available in quantum espresso. So with the U parameter you can tune and get a much closer value to the experiments, which we are not getting in the case of MgO right now, or zinc oxide, anything which we can consider. Here I am showing some comparison since I mentioned this quantum espresso several times. So this is the one of the results which I was working in my postdoc. And what I want to show that these are the results obtained from WASP and quantum espresso. And you can clearly see this blue one is the WASP result and the spectra is from the quantum espresso, and it is completely matching with each other. So using WASP or quantum X, which in the beginning slide I mentioned that which is much helpful. Both are will show equivalent results. It is depending upon which package you are familiar with. So, but in quantum espresso, there are a little bit options much little bit of sensor greater because of the V parameter which I mentioned. If you see the band structure, this is a particular system that is KV3SB5 Kagome system, and if you see the band structure also along this KMK symmetry path, the for VASP and quantum espresso are much agreeing with each other. The energies are lying absolutely similar to each other. So VASP and quantum espresso produce the same result which I claimed in the initial slide. Now moving on to the magnetic calculation. So the strongly correlated system comes when we are dealing with the magnetic materials or d orbitals or the f orbitals. So what we have to consider, we have to consider two different tags, that is the I spin 2 or magmom. So basically these two tags are important for the magnetic calculation. For I spin 2 is the spin polarized calculation. You have to mention this I spin 2. Once you mention this I spin 2, you will get the magnetic moment in these systems. So I can show you, I have done as a reference. For CO304, and if you see the relax, as Pankaj sir mentioned that it is antiferromagnetic in nature, and you can see I have chose, so here are much for the magnetic system I have used much more input files which was much lesser for the magnesium one, and it will take much more longer time to it for the iteration. So the main important tags are these two, I spin and magmom. And how we use this one magmom is, since we have this, if we see the postcard, so we have this cobalt, we have 6 cobalt. So we have this cobalt up spin, down spin, and this cobalt does not have any spin. So basically like that, we have used the magmon up spin, up spin, down spin, and this cobalt does not have any spin. And this is magnesium, this is oxygen. So once we did that, we get the magnetic moment, which is coming nearly S is equals to 3 by 2, which is cobalt 3 by 2. So this is the magnetic moment, this is the up spin and the down spin, and remaining 4 cobalts are 0. So if you want to cross check, you can give this certain values of this remaining 4 cobalts, but it will go to 0. That's not a problem. So like this, you can use this tags for doing the magnetic calculations. And this is the spin collinear, because we are considering the spin up and spin down, only two directions, but there can be possibility of non-collinear calculation. So it will take a much longer time to do the long collinear calculations, and in the non-collinear calculation we have 3 different directions, x, y, z. So you have to give the magnetic moment of one atom in 3 different directions, sigma x, sigma y, sigma z. So like this, I have mentioned only one. So here will be 3 components, here will be 3 components, here 4 into 3 means 12 components, and here 8 is 8 into 3, so it will 24. So it will be a large magmom line, and you have to just see for what tag for the non-collinear calculation we use. And this is now another thing which I mentioned earlier also, I just want to show for another work which we have done, that is the LDA plus U, that is the DFT plus U calculations. And these are the input parameters which we used. So if I see here in relax, so you can see these are the parameters we have used. So why we are using this one? We are using because we are dealing with strongly correlated system, that is the cobalt one. And how we have used that, here we have used the postcard. We have cobalt, 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 and oxygen. Like this, I have separated the postcard one. So basically, so here this is for the first cobalt, this is the second cobalt, this is the 4 cobalts which I have mentioned later, and this is the oxygen one. So the oxygen we don't need any interaction. So this is for L quantum number. So basically for D it will be 2, for P it will be 1, for S it will be 0, and if we don't want to consider any on-site coulometer, it will be -1. So since we are dealing with the D, so we have used this 2. If we are dealing with the P, then it should be 1, and for the S it should be 0. And if you don't consider anything, that will be minus. And this is the values which we have used. You can tune this value from 0. This is any integer you can put, but depending upon the integer, the system will behave, whether it is in metallic or insulator or semiconductor, what it will it happen. So basically here I have shown one work that which we have published, and here for u is equals to 0 we can see the metallic behavior, which is not true for this system. And this is the drawback which Pankaj sir already mentioned. For the strongly correlated system, these u corrections are important, and as I have incorporated the value of u, we can see the band gap gradually opening. And for u is equals to 4, we turned out that this is matching with the experimental band gaps which I have listed here. I have shown for CO304 and GeCO204, and it can give, and we can guess the possible transition, optical transition also. So this is important to how to fix the value of u. Another, there is a linear response method where you can compute and go to u, which is shown here. You will LDA u type 3. You can do that to get a certain value, but it is not so much confirmed that which u value will give you the correct lattice parameters or band gaps. So it is important, and for the strongly correlated system you have to use this, or it will not match with your experimental results. And this u, and here also I have shown for this with the quantum expression, the VASP, by changing the value of u, the lattice parameter changes. You can clearly see from, and we can consider the van der Waals corrections also, and we can see we can move close to these experimental values, as this one which I have rounded up is much closer to the experimental one with respect to the other values. And another thing, I just want to give a insight that how this U and V works. So this is, I just want to mention that it's a particular system. And here if we consider the value of U, means I have on side, this is the vanadium one, the blue one. And the inter site is in between these two vanadium, in these two vanadium, these two and these two. So basically this is U and these are V. So if you consider U and V, so both. So I just want to give a idea how u and v works. For that reason, if you see for u is equals to 0 and v is equals to 0, the band dispersion looks like that. But for, if I don't change the value of v, then we can see there is a wide opening. But if I give the value of v and don't change give the value of u, then the opening is close enough. So it merged. The M nature is not there. So basically we can see that u and v are working into opposite direction. So for many systems, this U and V are very important to pin it down the ground state of these systems. And lastly, this is some example which I want to give for a monolayer system and how to prepare a monolayer system. So if we take a bulk, here I have shown for the bulk material, and this is for Maxine. Here we will cut a Maxine one. So this is Ti3AlC2, and here this is the aluminium, this is Ti, this is carbon, and first what we do, we will delete this aluminium. I am giving an example to, if anyone is working on monolayer system, then they can try to prepare the monolayer using Vesta or anything which he or she is familiar with. So first we will remove this extra element which is aluminium here, and we will get this certain pattern, and then we will remove this periodicity. We don't require the other elements, we only we have to remove this periodicity. So we will cut this out, and this will prepare the monolayer of the system. So basically when we are working with a monolayer, so the two things we have to keep in mind: the in-car files will be same which you are using for your system, but the postcard we have to incorporate a vacuum, because there is only one layer. So we have increased. So it is 9, this is 3, this is 9, this is 27 Armstrong. So we are giving this vacuum. So nothing layer will interact if from the above. So, but we will not give any layer of the above, because in the K mesh we are giving this is a X, Y, Z. So this is the C direction. So C direction we don't have any K mesh. So this is only one layer which is going along X direction and Y direction. So basically we have to make two changes to do this monolayer system, the postcard and the K points. So this is the for the monolayer system. I am unable to show the calculations for the monolayer because it takes larger times, and the system which I have shown is relevant for this time. So first of all, I want to acknowledge all the works from the PhD which I have done from IIT Guwahati, and currently the funding which I am getting from Korea government right now for working here. So I just want to acknowledge my supervisors, Dr. Pankaj Mishra sir and Dr. Subhas Thota sir, for helping me to work in this DFT area. And this is my contact information. So if anyone need any suggest any help or anything, just feel free to contact me, and I will do my best to help anyone working in this area. So thank you for listening to me.
Thank you, sir. There are two questions that has been posted by the participants. First is, can I use P4 VASP on a Windows system?
Can you just speak out again? I can't hear you properly.
Can you use P4 VASP on a Windows system?
Can we do spin WASP in this system?
Windows.
Yes, we can do this PDOS. So basically, we can, as I saw for this, uh, mm, this is the contribution which I have shown for different orbital. You can do calculate the PDOS, and we have this L orbit 11 will help you to get the decompose of this DOS. So you can do that. It's not a problem.
I think the question was whether P4 VASP is available on Windows platform or not.
Oh, sorry. I heard that VDOS. Okay. No, Windows platform WASP you have to install in the cluster, and clusters are mainly familiar to this Linux environment. So for Windows, I think it is not available. Means you have to install in the cluster. You can't install in your laptop and do the computational. So you have to install in the cluster. And clusters are generally Linux based, so it is not possible.
The next question is, sir, what is the difference between SOC and EFT plus U in the case of magnetic system?
What is the difference between magnetic system?
SOC and EFT plus U.
Oh, SOC. So that is the spin orbit coupling we have to consider for the magnetic system, which system generally what happens that depend upon the system whether the spin orbit coupling is necessary or not. It completely depend upon the system. So you can consider the spin orbit coupling, but sometimes it is not necessary. And once the computational cost will increase when you consider this SOC calculations, the spin orbit couplings. But for magnetic, it is not relevant for all the magnetic materials.
Sir, I have one question. Can we perform any transport calculation on VASP?
Yes, we can do, as I mentioned. You can do the transport calculations, but here, as in the VASP kit, you can see that 68 is the uh, chance that you can extract the data for the transport. But for the transport, you need to calculate the conductivity, I believe. And the conductivity of which material you are calculating, accordingly, you have to give that I and V. So it is possible. But so you have to just I am unable to show the results, but I didn't work on that area much properly, but it is possible. I can tell that.
Sir, can you put it in the transport? Do you have any suggestion for that?
Your voice is cutting out, so I am unable to hear properly. Can you just speak it loud?
Okay, I was asking about electron transport. You calculate the ID characteristics.
The transport properties, I am not worked so much on that thing, but yes, generally what is possible, the conductivity is measurement is possible. You can calculate the conductivity of a system, and we can correlate with the transport from that way. But the conductivity is you can do. And if you need any help, I can we can talk later about this thing via mail or anything. But yes, it is possible. And truly, I didn't work so much on these transport properties, but there are papers which they do the conductivity using WASP.
Okay, thank you, sir. And another question is what are the limitation of VASP? Like where we should not use VASP?
So what is the limitation of WASP? Uh, Limitation one I already showed here, that the right now there is a new thing that the people consider that the zinc oxide material or the magnesium oxide material, which I have shown right now. Let me go there. So this is I have done using quantum espresso, but from the quantum espresso the band gap is matching. So this is, you can see from the DFT calculation, this red one is the DFT plus U, the dash one is the DFT plus U, and the red one is the DFT plus U plus V. So finally the DFT plus U plus V is giving much more better result, which is not possible in VARP till now. So it is possible in quantum espresso. So people are using different packages which are possible to, which are familiar, which are used to do. So suppose if want to do the mean field DMFT, so they are using wine 2K. So it depends. So which package you are using and what properties you are want to explore. So depending upon that, you have to use different packages. But yes, there are limitations of the VAS, which right now I mentioned.
The last question is, can we calculate thermal conductivity using VASP?
Yes, conductivity I right now mentioned, but thermal conductivity I have to check. I didn't calculate any time, so I have to check that one. I can't comment right now. I have to check, but hopefully it is possible.
Just now one more question came. If quantum espresso is free and we can do DFT plus U in quantum espresso, so why people choose RAS? What are its
The
advantages?
thing is, for the VASP, the pseudo potential files are much more reliable. Since the Quantum Espresso is free, once anyone go to this Quantum Espresso website, you will be getting nearly 10, 12 pseudo potential files, and which pseudo potential file will give you the correct result is it's very challenging. Since I have been working in this quantum espresso, it is little bit challenging. But in VASP, you have only one pseudo potential file, and that is much more reliable to any of this quantum espresso. So to get this result, which I mentioned, I have to tune the pseudo potential files of the quantum espresso to get much closer to the VASP. But in the VASP, we have only one pseudo potential for potassium, vanadium, and Sb. So that's why the WASP is much more reliable. But I am not saying quantum espresso is not reliable. You have to, because since it is free, you have to search out which pseudo potential is matching with your result. So you have to give that laborious job to find out the correct one.
Thank you, sir, for assisting the tutorial session. Participant has asked for your email address for any queries to be sent to. If you feel so, you can share that in the chat box.
So this is my email ID. I will share it. Sorry, just give a second. Did you get it? Hello?
No, sir.
I am typing it, but it is not going. I don't know what's the reason. Wait, just a second. I'm just hopefully. So this is my email ID. So I am trying to give it, but it is not going. There is saying message not sent. So I don't know why it is showing. Really sorry why it is not going. I am not able to understand. So you can just take a screenshot and just share in the chat box. It will help.
Yes, sir, they got it.
Thank you, sir, for joining us for the event. Now we'll take a break for up to 5:15 and gather again for the quiz session. So may I request all the participants to be present on time for to attend the quiz.
Okay, thank you. Thank you, everyone.
Thank you.
Thank you, Scott.
Welcome back, everyone. Now, okay. We'll move to the last part of the session. At first, I'd like to call our conveyance of the INUP program for the concluding and the board documents. After that, we'll start the quiz sessions.
So very good evening. Hope you all had wonderful lectures, informative, and you would have learned many things last 3 days. So before we conclude this workshop, we would like to give acknowledge the authorities of IIT Guwahati who helped us to conduct this event successfully. So in that part, we would like to acknowledge our Dean PRBR, Sir TKIR, and our Director, Professor Rajiv Ahuja, and IITG authorities who helped us in all the ways to get to make this event successful. Also, of all, we also thank Minister of Electronics and Technology for entrusting us this responsibility to in sponsoring this event, and we thank them especially. So we also thank our head Center for Nanotechnology and all the teaching and non-teaching staff associated with this center and their cooperation. Also, all the speakers who has delivered wonderful lectures throughout these days, and we thank each one of them. And we also thank Taksim for the university for helping us to give the demo of their software. And we also thank Center for Nanotechnology staff members, project staff, and the business scholars, and the anchors, everyone for their support in all the aspects. And we also, at the least, finally, we also thank all of you for registering this course and also participating actively in all the 3 days. All the 3 days for your and cooperation in all the aspects. So hope you all enjoyed wonderful lectures for 3 days, and now we will start this at 5:30. Do well in your quiz, and based on that, we will update you what is to be done in the future. So with this, we will conclude this conference, and we will move forward for in conducting the quiz. Thank you.
There are a couple of
Please ask him to check his-
They have already posted.
Ask him to check his connection.
Posted the chat box. Please note that you have to keep your video on during the entire duration of the quiz because it's required to take attendance. Another instruction is that please do not wait till the last moment to submit your quiz. Because often it happens that at the last moment you try to submit and then some internet connection issue will come. And therefore, you will not be able to submit on time. So please submit at least a minute or so before the end time. After that, there are still further any issues. You can please contact us through the email. Now, of course, the form will not be accepting any responses till 5:30. Okay, the quiz will start from 5:30 and then it will start accepting responses. So please wait till the time. Thank you. And good luck. We have updated the settings. You can now share your camera, open your camera.
अरे एकदम भैया एकदम बैठे एकदम
Okay, device fabrication is a class problem. Right? But another novelty is that we are also sensing SO2 for we are showing SO2 sensing.
The quiz link is working now. You all can start.